Right, that's how I talk about the two important processes in the early universe. The first one is the recombination, and the second one is the BBN, Big Bang nuclear synthesis. The recombinations is a formations of the atom, and after the recombination, the universe becomes transparent, so the photons can be propagated freely. So the CMB's cosmic microwave backgrounds that appears after such a recombination. And the recombination occurs at the temperatures nearby the zero point 0.1 electron volt to the 1 electron volt. The recombination process can be written as the electrons captured by the proton and the hydrogens and atoms by this during the such recombination process. The equilibrium density for the such a non-relativistic limit, mass is rather than the temperature. The equilibrium density can be written like this for each component, proton and electrons and the hydrogen, with the degree of freedom and the Boltzmann's factor with the chemical potential. And from this process, in the equilibrium process, the chemical potentials has a baryon relations for the proton, electrons, and the hydrogens atom, and the protons has a zero chemical potential because it is the mass lost. So by using the such relations of the chemical potential and using the sum of the fact, first of all, the number density of the electron and the protons are same for the neutral electric neutral universe, and the degree of freedoms of the proton and the electrons are 2 for each spin, and the degree of freedom for the hydrogen is the 4, and the mass of the proton and the hydrogens are same, almost similar. Electron masses are negligible, and the binding energy is the initial mass, protons and electrons minus the hydrogen atoms. So the hydrogen atoms are more stable tight. So such a binding energy is known as the 13.6 electron volt, which is electrons captures energy in the chemistry. So the in the equilibrium density of the hydrogen atom and the electrons can be the related as a function of the temperature, binding energy, and the mass of the electron. So the point is the number density of the hydrogen is proportional to the number density of the proton and electron. So that if there's many electron and protons that are prepared initial state, then the number density of the hydrogen atoms are also large, and if there's such a Boltzmann suppression factors with the binding energy is large, then such hydrogen atoms made in the with the many quantities. So and we want to know that how many the hydrogen atoms are made, and also how many the electrons are captures. It can be expressed by the such as the quantity free electrons fraction x, which is defined as the ratios of the number density of the electron and the baryon. And our goal is the free electrons fractions x is similar to the 0.1. So 90% of the electrons are captured by the proton, and it becomes the hydrogen atom. By using the some additional relation, first of all, the ratios between the baryon number and the proton number after to express the baryon asymmetry of the universe. And the proton's number density is given by the relativistic limits of the Bose-Einstein's equilibrium distributions, and the number density of the baryon can be written as the summation of the number density of the proton and hydrogen, and the number density of the protons are same with the number density of the electrons, because the universe electrons electric neutrals and radii. So the such equations, above equations, that can be rewritten by using this uh, relation. First of all, we know that this quantity multiplying such a baryon density, and we can replace the baryon density as the quantity atom, and there will be the number density of the photons will be appear. So insert such a number density of the photon, then such a factors of the 2 zeta 3 over the pi square terms will be appear. So on the second one is the such a quantity, hydrogen density, electron density scale, and the baryon density can be written through with the free electron fraction by using this relation. So this number density of the electrons is the X scale, and the number density of the hydrogen atom as 1 minus X. So this is a X scale and B scale, and this is a N B minus N E. So the 1 minus X times MB. So the such MB factors will be the disappear. So this equation is called the Saha's equations to determine the how much the electrons that captures. So our goal is the X is equal to 0.1. So first of all, there are many photons. So the eta is becomes very small. It means that the such many photons can ionize the atoms. So to make the 1 minus X is similar to 0.9, such exponential factor should be the large. So the temperatures should be the smaller than the binding energy. So to make the free electron fluctuations becomes 0.1. The temperatures of the recombinations nearby the 0.3 electron volt, which is small compared to such a binding energy. If we use a relation between the temperatures and the last shift and the time, the last shift is given by the 1320, and the at the 29,000th year, 29 times 10 to the 4 years, the recombinations occurs. And also we can calculate some of the other process. First of all, the Compton scattering or Thomson scattering as a photon last scattering, and such a process scattering between the electrons and photons will be stopped when the such scattering light by the multiplying the number density on the scattering cross section. If such a scattering light is same with the Hubble expansion light, the such as competence and the atom scattering processes that stop, so photons are decoupled, and such a photon decoupling temperature is given by the 0.27 electron volt, and the quite lighter than the recombination, and the decoupling last steps of the photon decoupling is given by the 1300, and the time is the 330th times 10 to the 4 is. So the universe becomes a transparent after the such a photon decoupling. And also the one most important stars is the link combination stop. Such a process, protons and electrons becomes the hydrogen atoms. The electron captures such a process. Later of such a process becomes similar with the Hubble expansion light at the temperatures nearby the 0.24 electron volt. So, So The recombination stage is electron fluctuations nearby the 0.1 electron volt, and at the decoupling, such as electron fluctuations and the hydrogen atom number densities will be the biggest. So maybe the our finish is the recombinations explanation of recombinations, and maybe the next time we talk about some radiation dominant to the transits the matter dominant, and the transits the dark energy dominant, such as the transitions between the each component dominance that occurs the someone is the before the such a recombination, and the someone occurs after the recombination. And the next times also I will talk about the Big Bang nuclear synthesis. This Big Bang nuclear synthesis is also important evidence of the Big Bang, and the calculations, the process is quite similar with the recombination. There's also the equilibrium density, and the how much the nucleus is made is in the early universe. So the points of the today discussions is recombinations in the early universe, and the hydrogen neutral atoms that made this, and after the photon decoupling also I want to mention that there will be the CMB strobe disappear as a cosmic microwave background, and the in the another videos that I discussed as the such as CMB anisotropy, and how the cosmological perturbations affects such a cosmological microwave background.